Hello. In the previous tutorial we implemented a simple model of vector alignment on a 2D plane. Today we will experiment a little bit with this model using GLSL and ShaderToy website, and I'd like to focus on visualization aspect of our model. So previously we were working on simulation shader, and now we will develop the visualization shader, and I'd like to show some powers that you get when you decide to implement all visualization with GLSL starting from scratch rather than relying on a third-party library. The first thing I want to add is ability to zoom into some regions of the grid to explore the neighborhood of those singularities in more detail. So with the ShaderToy you get access to inputs through textures or through uniforms. Uniforms are something like global variables that can be read by shader programs. So there is a uniform called iMouse that encodes current mouse position, and I'll show how to use it to implement a simple zoom effect. With this code, I now made the shader to zoom 4 times when the mouse button is pressed. So, for example, I want to look those two singularities a bit closer. I press the mouse and move them to the center of the viewport. And the way I do this is I create a variable that determines the lookup coordinates that is used by every pixel, and if we are not in zoom mode, this coordinate is just equal to current pixel coordinate, and we use it to compute UV coordinates. Otherwise, we do some simple coordinate transformation. We bring origin to the center of the viewport by subtracting the resolution of the screen divided by 2. Then we divide the coordinate by the zoom factor that we want to get, so that every screen pixel now corresponds to 1/4 of the grid pixel, and add the coordinates of current mouse pointer so that we look up to pixels that are located around the current mouse cursor. Then this way we can implement a zoom effect. Let's increase the zoom factor a few times. Now when the zoom factor is equals to 16, we see that there is a bilinear interpolation applied to texels when we look them up. Actually, I'd like to explore the states of individual pixels of our model, so I'd prefer to use nearest neighbor interpolation. You can do this by clicking this settings button and changing the parameters of particular sampler. And now we see that we can see individual pixels, but those pixels are now represented with colors, and those colors encode the directions of vectors stored in those pixels. So this is not very intuitive, and I'd like to visualize those directions as little arrows. But before proceeding to that, let's appreciate a little bit the compactness of implementation. So it took us just 3 lines of code to implement zoom that works at 60 frames per second, and I suspect that if I was using some external visualization library, it would probably take a comparable amount of code to just explain the library what do I need. But now let's try to make some arrows. We want to draw some glyphs in the center of every pixel in zoom mode. So let's increase zoom factor a little bit more so that we could see individual pixels better. And now I'll show the internal coordinate system of each pixel that we will use to determine the color that our shader produces. So let's just assign fragment color to the fractional part of grid position. We are assigning red and green channels and return, so that we don't do anything if we are in zoom mode. Now we see that on zoom every pixel turns into this gradient, where red encodes x coordinate riding from 0 to 1 and green encodes the y coordinate. So now each pixel is essentially a tiny screen, tiny coordinate system that we can use to paint something inside of this pixel. In GLSL we don't have predefined primitives to draw triangles, rectangles, but there is a very compact and convenient way to draw them that's called signed distance fields. If I search two-dimensional signed distance fields or 2D SDF, the first two links are pretty useful. The very first link is a collection of 2D distance functions made by the ShaderToy creator, and I'll just copy one primitive from this list. This is a function that computes the distance from a point to an isosceles triangle, and when point is outside of triangle you get a positive value that encodes the distance from the point to a boundary of triangle. Inside you get a negative value that also encodes the distance to a triangle boundary. So I'll just copy this function in our shader and use it. There are some good tutorials in the internet that you may want to read if you want to understand the math behind signed distance fields, and also the flexibilities that you get when you, for example, combine those signed distance fields and use them for manipulating the shapes, making smooth transitions between shapes. So I'll leave links to some good tutorials in the video description. But now we can try to make a tiny triangle inside of every pixel. Now every cell contains a tiny white triangle when we are zooming in. This line computes the coordinates of the current pixel inside of the cell. Note that I have set the origin to the center of the cell. This line computes the signed distance from the triangle to the current pixel inside of that cell, and this line converts this distance into 0, 1 value, where zeros are assigned to pixels outside of triangle and ones are assigned to pixels inside of the triangle. And finally we add this value to current fragment color. Now I'd like to rotate them depending on the vector stored in every pixel, but also I want this arrow to be a little bit longer. We see now that when we zoom in, every cell contains an arrow that corresponds to the direction vector value stored in this cell. I'd like to mention that those vectors are defined, given the nature of our model, up to a global rotation or mirror transformation. So when I construct per pixel per cell rotation matrices, there wouldn't be a mistake if I, for example, used left multiplication rather than right multiplication, or used a transposed rotation matrix. It would still produce the correct vector field in terms of our model. Before using the visualization we've built to explore our model, I want to show another neat trick for anti-aliasing of sign distant field represented shapes. If we zoom in, we see that our triangles are a little bit pixelated, which is not very nice, and there is a simple GLSL trick that allows to avoid that. Let's remove this hard thresholding with sign function and use another way to convert distance to color. We see now that triangles get a better anti-aliased smoother boundary, and the way we achieve that is by using f-width function. This function is a special GLSL function that computes the sum of partial derivatives of the provided variable with respect to x and y axes, and the way it does it is by communicating internally with nearby pixels in a 2x2 region and computing the finite differences. I'll give links to the tutorials that explain this in more details in the description, in the video description. Now, once we have visualization resume, let's look at our model closer. One thing that I found curious about the behavior of those cells, that those singularities that get attracted to each other and eventually annihilate seem to be moving towards their neighbors with tiny discrete steps. So all cells seem to be in the equilibrium, and then suddenly a few of them flip, centers get a little bit closer, and then everything is becoming static again for a few seconds. So in order to visualize those sudden jumps of directions in groups of cells, I decided to visualize the difference between the cell direction on current and previous iteration for every cell. You see, I modified the simulation shader so that it uses two last components of the cell state vector to store the previous non-average state of this cell. So what I've done now is I read the both previous value of both current value of the direction vector and also previous value of direction vector. I compute the distance between those vectors, and I just came up with some ad hoc formula on how to visualize this difference, amplifying lower magnitude values, suppressing higher magnitude values by power function, and I'm just adding this to all channels of the pixel color. And what this visualization gives us is that those relaxation events when two singularities are gradually coming closer to one another are visible as those pulses across the visualization of differences. And we see that even when the grid feels static now, there is a way for us to spot those tiny discrete events of vector state relaxation that's going on. This is all I have for today's tutorial. So we didn't do any rocket science here. The main purpose of this tutorial was just to show the capabilities that you get when you take full control on implementation of the model and on visualizing it with just a few lines of code, if you don't count the like function that we copied from the tutorial on sign distance fields. We managed to get a pretty advanced visualization that's running in 60 frames per second. Actually, it would have run faster if there was no this 60 frames limitation imposed by browser and by visual system. So I hope you enjoyed today's tutorial, and let's save the current shader so that we don't lose it. It's now available on ShaderToy for you to play with. Thank you.